Aloha, Richard Halverson here. This is ITS228, and today is February 3rd. So let me share my screen. And in the syllabus, we are right here. We're still in sorting algorithms. Now, I think I don't think I need to do too much more in sorting algorithms. If you look at the last video, it's kind of interesting because no one was here, so I took a chance and I pulled out all of the Python versions of all of the sorting algorithms that are in chapter 3, and I created one big program and I put in some code there to test which sorting programs were faster as the data sizes increased. And so that's a good video to watch. That's the last one. Let me show that. Let me show you which one I mean. But the technique that I used to set up this program to test the performance of the sorting algorithms based on the size of the data, that technique I'm going to have you use later, because part of this class, this is a third semester programming class for computer science, and so it's about algorithms and data structures and performance and performance as you scale. And so that's what this is all about. So, small scale, you might choose one sorting algorithm. Larger scale, you might choose another. One thing that might be interesting is when you use sort methods that are built into a language, you aren't specifying the algorithm. It would be interesting to try to figure out what algorithm what algorithm a sorting method in a particular implementation of a language, say Python, how it handles the varying sizes of data that it can throw at it. And I think that it actually looks at the data and chooses one algorithm versus another depending on the characteristic of the data. But anyway, so take a look at that sometime, and when the time comes when I'm going to ask you to use these kinds of techniques, I will refer you to this video, so you'll be sure to not to be left behind there. Okay, so I would like to today just start. So I've covered all the chapters, and I've also covered all the assignments. So if you look back in previous videos, you can see that in like this one, I think I covered the second assignment and so on. So pretty much I've got everything covered. So I'm going to start with chapter 4 today, but even though it's a week early, it's okay. Nobody's here. So that's good, because if I end up cutting this short, or if I there have been times, not in this class, but there have been times in the past when I've gotten 3/4 the way through a video and I went down a path that was the wrong path. And I think to myself, well, it might just be better if I don't post this video. And so that's happened to me before in the past. But anyway, I don't think that'll happen this time. So let's take a look at, this is 228. Are we still in chapter? This is okay. We're at the end. It's okay. Good. So I'm going to start with linked lists. What we would start next week. So that's chapter 5. No, that's chapter 4. Okay. So now in the beginning, we're going to notice that we talk about these abstract data types, but you scratch your head and you say, well, wait a minute, that's built into Python. And yes, that is true. But in other languages, that's not true. And you're not going to be programming in Python all your life. In fact, you're going to, no telling what language you're going to be programming in 3 years from now. So how would you implement this if you were doing it in any language? And so we talk about the list abstract data type and the things that can be created from that. There are singly linked lists, doubly linked, and stacks and queues and so on, and those have to do with standard operations that you do on the list and so on. So that's kind of what we're covering today. And I'm just going to go through the chapter and make sure you understand what each section is about, but then you have to click through this, and it may be just as simple for you to buzz through this if this all comes pretty easy for you, and you don't need to like watch the video. But again, as I mentioned before, one good thing to do is to with these videos, where is it? Let me get this big again. Oh, go click here. You know, you can, as you skim through the video, you can always just look. This textbook is great. You can just look right at the top and see exactly where you are. Here I'm showing you code. That's easy. You can follow that. And YouTube is good at letting you do that. All right. So a list is a common abstract data type for holding ordered data, having operations like append, removing an item, and so on, just like a regular list data type is in Python. Abstract data type, of course, means you think of it one way, but actually how it's implemented underneath is irrelevant or not particularly relevant to its usage. And of course, you can implement this abstract data type using even a standard array, and you just allocate a second variable to a second position in each in the array to identify the index of the next item in the list, and so on. We'll get to that later. By common operations, we mean like append something onto the end of it. It has an order to it. So for example, here you might say, okay, I'm going to create a new list called ages, and then you append some things onto it, and then you print it out, and it would print out the list one by one in the order that you appended it on. And we can remove things from the list. In this case, it shows you can remove the item from the beginning, from the right from the middle of the list. And so there's an example where if you have a big long list, and think of a list. So you have a big long list that's, let's say it's just a list of integers, and how is that implemented in the computer? Underneath, if it's implemented as an array, then if you're going to remove something from the middle of the list, you have to shift a whole bunch of things. You have to shift a whole bunch of elements, because now there's an open spot and you got to close that open spot. That's if it's implemented as an array, whereas you go down the list, you're indexing, you're incrementing an index. Whereas if it's another kind of thing where you have nodes and then you have a so-called pointer to the next node, then it's easy to take something out of the middle of a list, because you just find the thing and you unhook the pointer that points to it, and then you change that pointer to what the node that you're removing. You change the pointer to what that node is what the removing node pointer was pointing to, and then it's removed. And so that doesn't take a bunch of shifting. That's an example. So here, make sure you understand what it is. Here's a list of the common abstract data type operations: appending, prepending, we put it on the beginning, insert after a particular point. This is the list. This is an item in the list, and this is what you're inserting. And so you insert X after W. Here you're removing X from the list. Here you're searching for X, and it returns the item if it's found. Otherwise, it doesn't return anything, or it returns null. It doesn't really make sense to return an index, the index of the list, because we don't think of lists that way. Anyway, you can print in reverse order. You could sort the list. That actually changes positions. You know, the lists are mutable, and this is just a Boolean test. It returns true if the list is empty, otherwise it returns false. And this returns the number of items in the list. Standard basic things. Okay, singly linked list. For 4.2, you want to click through this. Here you have this is sort of a designated couple of variables that we call the beginning of the list. This is when you create an instance of a list. When you create a list, there's two variables that need to be allocated to manage the list. Two variables. One is a pointer to the head node of the list, and the other is a pointer to the tail node of the list. Now, you don't really need to have the tail node of the list if these allocation of these variables is expensive, like if it's in hardware, because you can always find the tail of a list by starting with the head and traversing down the list until you get to the end of it, until you get to a node that is pointing to nothing. But it's convenient to have the tail, because if you want to just stick something on the tail of the list, you can go right to the tail of the list and you don't have to traverse through the list. So anyway, that's and we will get to this node implementation, and we'll see how it is in Python. But anyway, given a character list C's next pointer value is null. Does it want me to put null here? I think it probably does. If I were to read the instructions, it'd probably say it. I'm going to try putting null here. C's next pointer. Yeah, okay. All right. So that's what you got to do for all these, and then you just get the points. So here's how you would append a node onto a singly linked list. You go to the tail, and then you somehow allocate a new node, and you take the next pointer of the node that is pointed to by the tail. You set that equal, instead of having it equal null, you set that equal to this new node that you're adding on, and then you change the tail to point to the new node. You'll learn that there's a particular order that these things have to be done, because you've got to keep track of things, and you don't want to accidentally change a pointer to an important node, and then you lose access to that node, because it needs to be pointed to by something else. So you have to keep track of that. Of course, it's a good thing that we're writing programs, because if you're writing code and you accidentally do that, then your program doesn't work, and you go, oh, I forgot to do this, and you didn't destroy a part or something like that. Which the thing about electrical engineering is it's the same kind of thinking. You're doing the same kind of stuff, especially sequential circuits. But unless you're simulating. But in the old days, we didn't have simulators, and we'd have to build the stuff, and you make a little mistake. So you shouldn't be afraid in programming. The thing that you got to learn, and maybe this isn't so tough for new programmers, but for old programmers it is. There's no penalty for running the program just to see if it works. And there's errors, but you want to start fixing the errors one by one. And you know that the compiler is going to tell you what errors are, so you just run the thing. And there's a certain discipline that we used to have to hold to when we were writing programs that you don't really have to anymore, which is kind of nice. Okay, this little symbol means it's the head of, this is the pointer to the head of the list, or the head value of this list called list. Anyway, so step through this and make sure you understand what all this is. Appending D to a nodes to this. updates which node's next pointer. If you want to append D onto this list, that's gonna update E's next pointer, because it's going to be appended right there. And so this is going to be changed. It's going to point to E. I'm going to put E. It's correct. And make sure you understand that. It doesn't take very much concentration, or it doesn't take very much study to understand what's going on here. And then after that, we're just building on the same thing. And so it's just, you know, all this class is about is learning all these clever things that other computer scientists have figured out and thought of, starting around 1970. Okay. Starting around 1970, I actually started taking my first computer science classes in college back in 1972, because I'm an old guy. And back then there were like, you know, there were like 4 or 5 computer science classes, and that's it. And then all the rest of the classes that you took were from the math department or from the some engineering course. And now, you know, when you go to Manoa and you look at either Manoa or West Oahu or Maui, and you look at all the computer science type classes that you can take, you know, there's like just dozens of, you know, just dozens and dozens and dozens of them, and they span all kinds of topics and applications. But anyway, and it's not that hard, so you know, you shouldn't be afraid of them. Of course, if you're taking 228, you're probably not afraid of any of this stuff. All right, so this talks about inserting, and this would be inserting inside like the middle of the list. Let's see, given the list after, type the list after the given operations. So got it. Okay, so we have this list 5, 9, and then we're going to insert after node. We're going to insert node 4 after node 9. Is that what we're going to do here? Let's see. So I would go 5, space 9, space 4. Now, yeah, that has to mean what that is. So I'm checking. Yes, it is. Okay, so make sure you understand that. So you have a list, you have node T and node Q. This thing assigns new node's next pointer with new nodes. Well, this is new node. This is the new node. And doing this operation takes this node and puts it, yes. See, the data is Q, see, so that's Q. Puts this after T, so it puts it after T. So it's going to put it in between T and L. And so this is new node. Its next pointer is going to point to L. Wait a minute. Okay, so that's what it will be, but it has to be described this way. Current node's next pointer is pointing to L. And I just said that after this is inserted, it'll be pointing to L, because this thing is going to be inserted right in here. And so we're going to take this node, this value, which is pointing to L, and we're going to take that value. We're going to take whatever this value is, it points to L. We're going to take this value and we're going to put it there. So now this thing points to L, and then this thing has got to point to the new node. So I'm going to say this. Yeah, let's say that. Oh, it's correct. Okay, good. And then this thing, list after node 1, insert node 6. Okay, so what statement does that execute, or this executes which statement. Okay, so so after node 1, you attach node 6. So we are, it is the current node's next pointer. This next pointer is equal to this next. After node 1 is node 6. Current nodes list head no, that's not it. New node next is equal to current node. List tail next is equal to new node. Ah, I bet it's this. Except for this should be a new list, shouldn't it? Or num list. Oh, anyway, this tail, the next pointer of the tail list. So in other words, the next pointer, this pointer points to this pointer right here is gonna should point to new node. So I think it's this last one. So anyway, make sure you understand that. Here's a challenge activity. Just step through this. It's 12:39. I'll do one of them. Num list 13. Okay. What am I supposed to say? Oh, what is this after that executes? It starts out like this. After 71, put a 50. So it's 13, comma, 71, comma. And then after 71, put a 50, 50, comma. No, I'm not going to put a comma yet. Put a 50. After 13, put a 60. So I'm going to put a 60 right here. 60. And then after 13, put a 31. So I'm going to put a 31 here. Okay, so I think that's what it is. Oh, look, that's what it is. Very simple. Okay, so make sure you do the rest of them. All right, what's next? Removing. This is how you remove from a linked list. So, you know, what this is following the links in your head, you know, and you gotta make sure the order is correct. Okay, so what is this gonna do? I'm gonna run this and see what it does. What are we gonna do here anyway? Are we gonna remove something? Let's just keep going. Oh, that's oh, I see. We removed something. We removed what was there. All right. Next, we're going to remove after list remove. Move after. Okay, let's see what this does. It's going to execute. Oh, we're executing. We already executed the first one. That's the problem. Then we're going to do that. And okay, I guess we're removing 4. And so what we need to do is we have to figure out what 5 points to, because what 5 points to, no, let's keep moving here. We remove 4. Oh, okay, let's just keep moving here. I see, we were removing 5. Oh, I see. I misunderstand it. We are removing the node after 4. Can I start over again? I'm gonna start over again. Okay, so the first thing I'm gonna do is I'm gonna remove remove after null. Let me see what this does. Oh, remove after null must remove the first item in the list. Remove the lists. Okay, so remove after operation, after existing node. If the current node is null, remove after removes the, if the current node is null, in other words, if this parameter is null, then it removes the first item in the list. So that's what we're supposed to learn from this. So we're supposed to see how these execute. The first one is going to remove the first item in the list. The second one is going to remove the node after node 4, which is this node 5. And then after that, it's going to remove the node after node 4 again, which means it's going to remove this node. So what's going to be left, I guess, is 7 and 4. So this one is going to first remove the first node, and what it has to do is take what was in next and stick that in head. Okay, so now next we're going to do this one, oops, node 4, and so what we have to do is we're removing the node after node 4. So we have to find out what that node points to. That's node 5. So we find out what node 5 points to, and we take that value and we put it in here. And then that effectively takes 5 out of the linked list, out of the loop, you could say. So that's all this does. So we're going to remove what the one that's after, and so it sets that one. It figures out what the one after the finds out what the next value is in the node after it that it's removing, and it points to this node, SUCNODE, and then it takes that value and it puts it in here, and then that effectively removes the node. Okay, so you can do the rest of them. Make sure you understand this. Here, given num list remove after, we'll remove what's after node 55, executes which of the following statements. Which of these statements is executed when the operation of removing 12. So the first one is the successor node is going to be pointing to 74. The successor node list head next. Is that the successor node? No. This one, current node, current node, list head. Well, I don't know the answer to these. So I'm going to just list head next points to this node. Current node is not null, so the list's head node is not removed. That's right. Okay. For the list, okay. Current node the current node must be this. And so the next, I would say that's no also. The successor node exists. So node 55, next pointer is pointed to 72. I guess I'm not understanding the question here. The successor, okay, so it's removing after node 55, which is, we're removing 12. So, after current nodes next is equal. Okay, so yes, I see that this is. So current node is going to be pointing to this 55. And after this thing executes, then the next pointer of the current node is going to be pointing to the successor node. And the successor node is going to be this one. So yes, that's why this is yes. Okay, list head is going to equal to the successor node. I don't think so. And list tail is going to equal to the current node. No, I don't think that's going to be true either. All right. Well, make sure you understand these. Here's a challenge. I'll do one of these, I guess. Given this list, what list results from the following operations? Well, okay, so start. Okay, 9's not going to be there. The node after 7 is going to not, 8's not going to be there, so 7 will be here. 8's not going to be there. And so 4 will be there, but 5 will not be there. Okay, and 3 nodes are removed. It starts out with 5 down to 3, so I'm going to check and see if that's correct. And yes, it is correct. All right, searching a linked list. That's simply, you can't do anything but incrementally go through the list, because you can't do a binary search or anything, because there's no way to get to the middle, or even if the list is sorted, there's no binary search way to find something if you're looking for it in the list. If you want to do something like that, you make a tree, and we'll get to that later. But it's a binary tree is like a linked list, except for instead of each node linking to only one other node, each node links to 2 other nodes. Anyway, so given a search algorithm that returns a first node whose data matches the key, or returns null if it doesn't. Okay, so this is simply, you start with the list head, start with this one, you test to see it if it's null. If it's not null, then look at it. And here we see, look at the data, and if that's equal to the key that we're looking for, then we say, yeah, we found it. So we return, the pointer to that list. Otherwise, we go on to the next node. We go to the next one and we test that one. And if we get to the end, then this is going to be null, and we end up returning null because we didn't find it. So make sure you understand that. Pretty simple. Searching this first assigns current node to M, because it starts at the head. All right, so make sure you understand that. Here's a challenge. Oh, there's only 2 of these challenge activities. Okay, so for this one, we are doing something like searching a list that this method will search this list for value 43. Search points to the current pointer to node. Okay, so so what this is asking for is, okay, so it's executing this statement. Okay, while it's executing, it's going along, bum, 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 and okay, so after checking node 24, the current pointer is going to point to 30, is going to point to 35. Okay, so that, okay, I'll tell you, I'll just do this one. You can do the next one. So it's executing this statement where it's looking for this one. And by the way, the answer is going to be whatever this is. Whatever this is the answer, because it's executing this, and it's supposed to return a pointer to this. And the only place where there's a pointer to that is right here. We don't count this. Okay, this is only used if you're going to add something onto it. So we say after checking node 24. Okay, so what this thing does is it checks it, and then if it's not it moves the current pointer to. Let me just do this one. First assigns the current pointer to M. Oh, I did that one. So okay, great. Okay, so after it's done looking, after it's done checking out 24, that because just, you know, when it's checking out 24, the current pointer is pointing to 24. But just after it's going to do that, okay, so after it does that, it sets it to 35. So I'm gonna, what am I supposed to do? Put 35 here. Am I supposed to put 35 here? Or am I supposed to? I think I'm supposed to put 35 here. I'm gonna put that. I'm gonna put 35 there. Okay, and then it'll make it totally. It'll make how many comparisons? Well, it's gonna make 1, 2, 3, 4, 5, 6. So I'm gonna say 6. Yes. Check it. Hey, all right. So you can do the next one. Okay, now here's implementing singly linked lists in Python. So we can start out by constructing constructing the node and list class. Okay, so in Python, classes are used for both linked lists and the nodes that comprise the list. Each class includes references to nodes and a head and tail nodes. Okay, so we're going to define this class. First, we're going to define a node, and a node is simply something that holds some data, and then something that points to the next node. And so this is going to point to another node. How do we say that? I guess it doesn't matter until we assign the first one. Okay, so a node class has 2 members. Yes, it does. True. The data value of a node is set to none if the node is not in a list. No, I don't think that's right. The data value of a node is set to whatever the data value is. So this is false. It sets the next value of the node is set to none. Okay, so anyway, this is false. An empty linked list has a single node with a data value of none. No, that's not true either. That's false. See, so we're 2 classes. There's a node class and there's a linked list class. And a linked list class is simply it's got 2 values in there. It's got 2, you know, attributes or 2 fields, 2 variables, and one is going to point to a head node and the other one's going to point to a tail node. And so this is how you create an instance of it. Here's how you create an instance of a node with a value, which is going to have next of none. Let's see how we So appending a node to a singly linked list. Okay, so so let's say we have a node. Append method. Append method is a method within a linked list class. The append method adds a node to the end of the list, making the node the tail of the list. The append method has two parameters, the second of which is the new node to be appended. The first one would be the list itself, and this is a method that you execute it by having the name of the list dot append, and there's just a new node in there. So here we have a couple of nodes, and we have a list called numList, and here we can append node A onto numList, and then we can append node B onto numList. And so when this is done, it's going to be a single list with 95 being the first one and 42 being the second one. So an appended node becomes the head. Oh, an appended node becomes the tail of the linked list. So when you're appending a new node, it becomes the tail. It's added to the tail of the list. Now, if there's no nodes in the list and you append a node onto the list, it's also going to be the head of the list, but after that, appending a new node will only be appending onto the tail. That's what my answer is. Which statements append a node with the data value 15 to the num list? Let's see. Which statements append a node with data value 15 to the num list? Well, it would be this one, because the name of the list is numList, and the way you use the append function with numList is you say the name of the list dot append, and then you put, it's the single identifier of the node that you're going to append. The self, you don't put the self there, you put the self in the definition of append, but you don't put the self when you're actually using the append method anyway. It's this one. This is my answer. All right, append singly linked list method, additional methods. Okay, so here's prepend. Looks like you can put it on the beginning, puts it. Okay, so it checks to see if there are any nodes in the list. If there's not, it just attaches, it points both the head and the tail to this new node. But if there is already nodes in the list, then it's going to make it the first node. So it's going to take, it's going to make the next field of this new node equal to what the head field was of the list, and then it'll set the head field of the list to equal to the new node, or set point to the new node. So that's prepend. This is insert after. Insert after means it's going to go down the list until it finds the after, and then it's going to find which node to insert after, and then it's going to insert it after that. So inserting it after that, we saw earlier, you find out what the next value is. You set that equal to the new node's next value. You set the next value. Anyway, you saw that up above. This is removing, same kind of thing. Here is a okay, so here's a program, and what I will do next time, I'll put all the juicy coding stuff in the next video. So if you don't, so maybe if you're just interested in having some help going through the chapters, going through the sections, you can watch this video. But if you're more learn by hands-on coding, we'll wait to the next video. And what I'm going to do is I'm going to take a lot of these Python things here, Python singly linked list, doubly linked lists, traversing through the lists, sorting the linked lists and so on, and traversing linked lists but using recursion. I'll talk about all those. I'll make a program and throw all those Python, all that Python code into a program, and we can execute and see what it's like. All right. Now, doubly linked lists. I'm not going to go through the whole thing with doubly linked lists, but as you can imagine, a doubly linked list has one more link to a node, and it's a backlink. So a doubly linked list, if you ever add a node, you can go to the next node, or you can go to the node right behind it. The singly linked list, you can't easily go to the node right behind. If all of a sudden you find yourself at a node and you want to go back one, and you're in a singly linked list, you can't. You have to go all the way around, and somehow you have to know, when you're at the previous one. But with a doubly linked list, there's a second link that's got two links. Each node in a doubly linked list contains data and two pointers. Given a doubly linked list with nodes ... the node 20 is the head. Yeah, isn't it? Given a doubly linked list with these nodes, node 7's previous pointer points to 4. Given a doubly linked list with nodes node 7's next pointer points to 3. All right, and so appending, so now these kinds of functions are a little bit more complicated because you have a lot of pointers that you have to keep track of. You have a lot of pointers that have to be reset. If you're adding a new node in there, you got to set all the pointers for the new node. There's a particular order that you have to change these next and previous pointers. So go through these exercises and make sure you understand that. These are exercises on how you append something after node 5. So anyway, I'm not sure what this is. It looks like, let's see what the, okay. Call this node 5 executes which statement? Does this append onto the beginning of the list if it's not there? Is that what this does? Appends to an empty list. If a list head's pointer is null, an algorithm points the list's head and tail pointers to a new node. Append. Yes. All right, so anyway, you should go through these. Let's go through one of these. So we're going to append. Okay, I guess this is going to append onto the end. So this one here, I'm looking at this one here. It's going to append the 5 onto the end. So the first thing that has to happen is the list head doesn't need to. We are appending it onto the list tail. List tail next has got to point to the new node. Yes, this is true. The new node's going to go here. So the tail next is got to point to the new node. And okay, that's the answer to that one. Let's do this one. The list append inserts node F after node N. The pending node K executes which of the following statements? Okay, we're going to append node K. List head equals new node. That's true. List tail next equals, that's not true because list tail is not pointing to anything. So this is, there's no next here. New node previous, no, you don't. If it's a brand new node onto an empty list, there's the new node is not going to have the new node's previous list is not going to point to anything, although this is true. I'm going to say it's this one, but it could be this one. Now, what happens if I say this one? The list is empty, so the list tail node does not exist. Well, the list tail node is equal to null, and the new node's previous value is going to be null. But I guess when the new node is instantiated, then it's going to be null anyway. So yes, of course, it's this one, because that in effect has to be done. That's an operation that has to be done. This is effectively true, but it doesn't. It's already that way. So anyway, prepending a node to a doubly linked list. Okay, prepending means you're sticking it on the beginning. So go through that. Make sure you see that in your head. Here's a challenge activity. Making sure that you understand this should be very similar to the other one because this is just the outcome. Okay, and this is inserting into a doubly linked list. It's more complicated. See all these operations that need to be done. There's 4 different links that have to be set. The new nodes next and previous have to be set, and the current nodes next has to be set, and the successor nodes previous has to be set. So that's what this is. And here's a nice dragging thing you can do. And this is removing. And so go through that. And we have some Python here. Yeah, the next one is Python. And so here's what Python code looks like to implement doubly linked lists. Here's all the methods and so on. And so next time I will take these algorithms, take these programs, and code them up into a single program and figure out how we can run some tests to compare performance and so on. So anyway, this is I've covered chapter 4 up through section 410, and I will see you next week. Thanks for watching.